Hello, everybody. Welcome to another discussion in dynamics. I hope you're doing good. Okay, today we have a lot of things to do. So without further ado, let us jump straight into our discussion, okay? So this is planned for today. We are going to do, again, brief lecture review, and then these two problems. I am pretty sure, I'm not like 100% sure, but I'm pretty sure that we won't have time for this guy. Example number 3, okay? So please check the solution on Canvas, okay? And topic of today is normal tangential coordinate system. Okay, so as I said before, without further ado, we are going to start. Okay, exactly as the last time I prepared something before our discussion, okay? Today we will compare Cartesian coordinate system, polar coordinate system, and normal tangential coordinate system. To be honest, we are just going to focus on this thing today, okay? Because you guys know that Cartesian coordinate system and polar coordinate system are one of the ways to describe the motion in 2D, maybe even in 3D, yeah. However, and they have like something specific about themselves, yes? So first of all, one more time, Cartesian coordinate system, we use I and J, unit vectors that are constant, yes? In polar coordinate system, we use UR and U theta, unit vectors that are not constant, yes? And we talked about them last time. Today, we will talk about normal tangential coordinate system, and we use these two unit vectors to describe the motion, UT and UN. Again, they're not constant, and again, their first time derivative is not zero. Okay, we will talk about it more in a second. The story goes like that. We have exactly the same trajectory, okay? It's exactly the same motion, and nothing changes. Our particle P follows that trajectory. And it has velocity, that blue vector, okay? And we define ut that is aligned with velocity, okay? So I'm just going to write in here, v is equal to v times ut. I don't know, plus, of course, 0. Don't write it even, yeah? 0 plus un, yeah? But if it's basically 0, so I'm going to erase it, okay? All right, so just to prove you that that vector changes, that ut and un change their position, their orientation, just to prove you that they are not constant. So let's say that this is situation, our point P is here at, I don't know, time instant, let's say 2 seconds, okay? Let's say that at time instant 5 seconds, our point P will be here, okay? This is time instant 5 seconds. So our velocity, let's say, will be pointing this way. Yep. You can clearly see that ut changed direction. And un as well. Un will be pointing this way. Always inside the curvature, inside that oscillating circle, okay? Let's say that at time instant 9 seconds, point P will be here, yeah? And let's say that our velocity will be pointing this way at time instant 5 seconds. Again, our ut changed direction, yes? It is always aligned with velocity vector. And I believe that curvature here is something like that, yeah? So un will be pointing this way. Un will be pointing this way. Okay, any questions so far? This is one of the ways to define the motion. Okay, thinking about questions, I'm gonna continue, okay? So definition does not change, yes? Acceleration is always first time derivative of velocity vector. So I'm just gonna plug this guy here. And this is a product rule. Okay, So this thing is clearly V dot. And believe me or not, but this guy is none other than V divided by rho UN. I would like to prove it to you. However, we don't have time for that, yeah? And it's not required, unfortunately. When I was taking dynamics or advanced dynamics, all the derivations were required, and they could be on the exam. Yeah, in here we just give you examples to solve. So if you wanna see the derivation, come to my office hours, okay? So this is our acceleration expressed in NT coordinate system. V dot ut plus v squared over rho un. Okay, so this is how we describe the motion. There was a good question of, I believe, Atal after last discussion, because Atal approached me and asked me how to find the magnitude of these two vectors. It's clear, yeah. So in normal tangential coordinate system, magnitude of V is basically V, yeah? It's just V. And magnitude of A is equal to V dot square plus V to the power of 4 divided by rho squared square root. Yeah, I just took a magnitude of this vector pointed by green arrow. Yeah, this is magnitude of that vector. Any questions? Anybody surprised? Confused? Me, but I'm always confused. There's maybe one more. You should have one more question. Usually, there's that every single semester is the same question. We defined velocity. We defined acceleration. How about position? Yeah, Will. And your name is Will. Yes. Okay. What's the answer? How to define position in this coordinate system? Anybody want to give it a try? You can be wrong. Yeah. There is easier way to do it, but I don't know your name actually. What's your Scott? Okay, Scott. This is point P. What are the coordinates of that point in the red coordinate system? 0. Always. Yeah. How about this? How about point P here? Point P is always coincident with the red coordinate system. Do you see it? Yeah, it's always 0. So we just don't, or actually, we don't define it. Yeah, it's 0, whatever you prefer. Or we don't define it. Or we don't define it. Do you see it? Okay, guys, I have nothing else to say. Any questions? Did I forget about anything? Okay, examples? Do you want to see? So this is theory. Now let's see how to use it, okay? Please familiarize yourself with the problem statement before we start our solution. All right, so what do we have in here? First of all, we know that our particle starts from here, yeah? So this is a rope at the beginning, here, and our particle starts here with velocity v0. And by the way, at every time instant of our motion, velocity will be constant. In here also, velocity is equal to v0, okay? This is our trajectory. So we can basically see that our rope wraps around the drum, yeah? It wraps around that circle until the heat occurs, yes? So it will basically, I don't know, when particle can be here, particle then can be here, yeah, until it hits the drum exactly here. So I said about velocity, and I believe that we know all the geometry. Yes, we know the radius of the cylinder, we know L0, and there is angle theta defined in here. And they ask us to find acceleration using these magical formulas. Yes, we just derived. And after we do that, they ask us to bring it to Cartesian coordinate system. Okay? So let's do it. So first, let me write down this expression. A is equal to v dot ut plus v squared over rho un. Okay, guys. Question to you. What is v dot? Zero. Because velocity is constant. Exactly. Zero. Since velocity is constant. Great. So our expression simplified tremendously, yes? We won't have two components, we will just have one component. So our acceleration is for sure equal to v squared over rho un. Okay, so we know that v is always equal to v0, yeah? So it will be v0 squared un. And now I would like to ask you a second question. Can any of you find me expression for rho? What should I put here, basically? What is rho? Anybody want to give it a shot? Based on the drawing, by the way. Look at the drawing here and tell me what rho is. You mean this R? Not really. Yes, sir?
Well, starting at like L0 away.
Great.
Wrapping around. So like L0 minus something like R, like but as a function of theta.
Yes, very good. Okay. Theta R, exactly. Yes. Good shot. Exactly, yeah. And what's your name? Kyle. So what Kyle said is that rho, this value, is exactly this thing. This is the length of the rope. And he was right, because we start with L0, yes? At the very beginning, we have L0. Yes? And then we have that blue thing plus orange thing, that arc. Okay? And that the length of that arc is exactly r theta. That's why he said L0 minus r theta. Do you see that, guys? Okay, if you have any if you want me to explain it one more time, you can ask me later, okay? Thank you, Kyle. Okay, so I'm gonna put it L0 minus r theta, and this is the end of the problem, by the way. I mean, end of part A. So our A is v0 squared divided by L0 minus r theta un. Okay, so this is our acceleration expressed in anti-chords. Okay, so maybe let me draw it, okay? I would like to draw it. I think we don't need that, we don't need that. We don't need this. We don't need trajectory. I think if I draw it from scratch, it would be faster, don't you think? Yeah. So I wanna draw this vector here. Okay. So first of all, I will define ut and un, right? And I see that our a, which should be vector, is aligned with un only. Yes. So our an points this way. So our a points this way. And that's all. Yep. And why I did that drawing? Because I just would like to smoothly go to part number B, where they ask us to express it in I and J. Now, part B. Express A in I, J. Okay, so I believe that we should do some projections here, yes? Because we just have to project our A on these two directions, yes? So we will have AX and we will have AY. Right? Any objections? And to do that projection, we need to bring that angle theta somewhere in this triangle, okay? So let me do it quickly. I'm gonna switch the color, maybe to orange. So I think that we have something like that. I think that we can also have something like that. So if theta is here, I believe that this angle will be 90 minus theta. Yeah? That also means that this will be theta. Yes? That means that this is 90 minus theta. So that means that this is theta here. This thing is theta. Okay, and now we see that our AX is A, sine or cosine theta? Anybody? That would be sine, yes. Sine theta. And this guy has no other choice. A cosine theta. Okay, so we see that our acceleration is A sine theta, A cosine theta, yes? I did a small mistake in here because I forgot about minus, yes? Our AY points in the negative direction, yes? So I should put minus in here, yep? So in other words, this is equal to, maybe, this is equal to V0 squared, L0 minus R theta, sine theta minus cosine theta, 0. This is expressed in IJK. This is expressed in, and by the way, this will be our A expressed in NT. So that would be 0, V0 squared, L0 minus R theta 0 in NT, in T and K, sorry, T and K. T and K. Okay, any questions? Who is confused? Besides me.
I just want to make sure you put the negative on the A cosine theta because it's going negative by J direction, right?
Mm-hmm.
Okay.
Yes. Yeah. Will?
No, I think I got it now.
Well, what was the question?
I was going to ask the same thing.
Okay. I don't trust you. I don't believe you. But okay. Any other question? How much time do we have? We have like half an hour more, yes? Okay, so let's maybe draw quickly this one, but like 1 minute, okay? Let's draw quickly this thing. Magnitude of A, okay? So let's draw our A as a function of theta, okay? So I believe that we will start with v0 squared divided by L0. This is our initial acceleration, yes? And this will be hyperbolic function. So it will look like that. Yeah, this is heat. This is our heat. And our heat occurs at this angle. I bet you all guys know how to find it. This will be theta star equals to L0 divided by R. Yeah, so heat occurs at that angle. Yeah, and this is our magnitude of A as a function of theta. For the last time, questions? Are you confused? Okay, nobody answered. Yeah, so if you're not confused, let's do example number 2, okay? We will see what will happen. Yes, I can. Yeah. And by the way, this is all recorded on YouTube, yes? So you can also always play the video on YouTube and you can copy that drawing from there, okay? I would like to go to another example because I am very scared that we are going to run out of time, okay? Please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have our plane that is, we're gonna model it as a particle, okay? Our plane starts from here. It has velocity v0, and it takes a turn of 90 degrees, okay? Along this trajectory. And it ends up here, of course, with velocity vf. Please observe, guys, that our osculating circle, yes, that defines the radius of curvature at different points of curvature, of trajectory, sorry, also changes. Yeah? We start with a big rho, and we end up with small rho. Okay, it also changes. What else do we know? Aha, we know velocity initial, which I converted from kilometers per hour to meters per second. And we know velocity final, and I did the same thing with it. Turn is 90 degrees. Oh, we know a good thing. AN is always 8g, okay, it's constant. This is a good thing. And by the way, they also told us that speed decreases uniformly. And you will guys translate it to me later into mathematical expression, okay? What they ask us to find is radius of curvature final and how much time does it take to that plane to take that turn, okay? Rho final and T final. Solution. Let me draw. This is how I solve those problems. I'm just gonna write those magical expressions we derived, okay? I'm not even sure if we're going to use the first one. I think we're only going to use the second one. Okay, So I can also write in here that this is AT, acceleration tangential, plus acceleration normal. Okay, and you guys can see that these guys must be equal, yes, to one another. So I can write in here, AT is equal to V dot, and AN is equal to V squared rho. Oh, I put rho squared in here. Sorry guys, my mistake. No square in here. Okay, so I believe that this is very fast. Let's find rho f, okay? This is fast, easy. We are just going to use this expression. Because we know that AN is equal to 8G, okay? AN is constant, and this is equal to 8G. So we can write 8G is equal to V squared over rho. And we basically have expression for rho. Rho is equal to V squared divided by 8G. Alrighty, how to find rho final? Anybody? Yeah, Kyle. Thank you. Yeah, because our rho all of a sudden is a function of velocity, yes? Only. Yeah. So let's just plug V final. So our rho final is rho of V final. And this will be equal to V final squared 8G. This is equal to, oh, cool number, 222.222 squared divided by 9.81. Okay, grab your calculators. Rho final is equal to approximately 629.238 meters. Great. 50% of the problem done. Questions? Questions? Will?
Why do we use V final?
Oh, because they ask us to find rho final. Yeah, and you can see that rho final, look at the drawing, rho final is associated with V final. Yeah, rho is a final of V, yeah. And you can also, by the way, if you want, you can find rho initial. Yeah, rho zero, just plug here V0. And you will see what is the radius of curvature. Yeah. Cool. Good question. Yeah. Anybody else? Okay, part B. Part B. Find TF. Okay. So I believe that we use this expression, yes? We use this expression in our part A. So how about using this guy in our part B, okay? I think we cannot squeeze anything else from the other expression. Yeah, let's now focus on the other one. Okay, so we know that AT is dV dt. Okay, and what can you guys tell me about AT? Is there? I would like to integrate. Okay, I would like to integrate like that. But can you guys tell me something about AT? Is there anything interesting about that thing? If you look at the problem statement, or here, this information. It diffuses uniformly, yes, thank you. And what does that mean? Yeah, AT is constant. Do you like integrating constant things? Yes, that simplifies problem tremendously. Yes, AT is constant because speed decreases uniformly. Yeah. In other words, AT will be linear function of velocity. I believe so. No. Okay, we'll see. Maybe I'm mistaken. Let's integrate. Okay, but we need integration bounds. So I believe that in here we will start from 0 and we will end up at t final. And at the time instant 0 we had v0 and we will end up with v final. Yes. So in here we basically have v final minus v0, and this is equal to AT times TF. Perfect, we found expression for TF. TF is equal to V final minus V0 divided by AT. Almost done, yeah? We know everything, but we don't know the value of AT. Yes, we know what is V final, we know what is V0, they told us, but we do not know this value. We don't know this value. We must find it somehow. Any ideas? Yes? Yeah, but we don't know total time. Yeah, they ask us, look, yeah, they told us to find total time. Yeah. So I will suggest something. Maya, do you want to say something? No. Yeah. So we integrated in time. Yes. We integrated over time. Yeah. So how about right now integrating over path? Let's integrate over distance. Okay. Let's integrate over that. You know the trick. I will show you. I will just remind you. Okay. So how about doing this? Wait a second. I will just make some space for myself here. So you guys know that AT is equal to dv dt, but you also remember our little trick: dv dt ds ds, yeah? And that was velocity. So we end up with another definition of acceleration: v dv ds. We are going to clearly integrate along the path right now. Okay? So let's do it. We have v dv is equal to AT ds. Okay. We are almost there because we do not know. We must express this ds in a smarter way. Okay? Because we actually do not know what is this distance. What is this distance of that arc? Okay, but we can maybe express it in a different way. So trick, or actually digression. Digression number 1. I don't know if I will have more, but I'm gonna call this one digression number 1, okay? ds is always equal to rho d theta. Okay? In other words, if we have an arbitrary trajectory, this is arbitrary trajectory, and let's say we consider this point, okay? So we can always draw in here that osculating circle, okay? That has rho, okay? And ds is that infinitesimal displacement, yes? ds is here. ds is here. This is that small vector, okay? By the way, I'm gonna redraw that rho. So rho is here. And our increment along that path is just defined by d theta, okay? That little angle is d theta, okay? That's why you can clearly see, guys, that ds is always, by the way, always rho d theta, okay? We're gonna use this geometrical trick, okay, to replace our ds with rho d theta. So I'm gonna write it here. V dv is equal to at rho d theta. It's not the end. Digression number 2. What is rho? We found it at the very beginning. What is rho? Is it a function of, I don't know, theta? Is it a function of velocity? I think it's a function of velocity. Do you remember? Rho was function of velocity. Let me copy paste it here. We found it here. Here. Yep. So I indeed had 2 digressions actually. Okay, so let's plug this one in and let's see what will happen, okay? So we have v dv equal to at v squared 8g d theta. Okay, so I must bring the other v squared on the other side, yes? Because everything with v should be on the other side, yep? So I'm just gonna do that. You should remember that from calculus, yeah? I bet you remember, yeah? So it will be dv divided by v, and this is equal to at over 8g d theta. Awesome. Now we can integrate. Now we can integrate. And you guys maybe can tell me integration bounds. I will start with the left-hand side. So we start with v0, and we end up with v final, yes? And I would like you guys, one of you, to tell me what integration bounds I should put there for theta. So v0 corresponds to what angle? 0. Okay, and if this is 0, so v final corresponds to what angle? Yes, 90 degrees. Let's speak radians, okay? So pi over 2. Perfect, thank you guys. Okay, so if I remember correctly from school, this will be equal to log natural of v final minus log natural of v0. And this is constant, by the way. Everything here is constant. So this will be pi over 2 at 8g. Yeah. Oh, and I also remember that this is like we can do like the thing to this expression. This will be actually log natural v final divided by v0. Yeah. Something like that exists in mathematics. Yeah. Okay. Let's find at. Yeah. Do you remember? This is the only thing missing. Yeah. Once we have at, we have tf. Let's find at from this expression. Let's find at from this expression. So at will be equal to 2 over pi times 8g times log natural v final over v0. Plug in values. 2 over pi times 8 times 9.81 times log natural. In here, it doesn't matter if it's in meters per second or kilometers per hour. The units will cancel out. So that will be 800 divided by 1100. Grab your calculators and obtain that our at is equal to approximately minus 15.91056 meters second square. Okay, we obtain a negative value. Does it make sense? I think it makes sense because our thing decelerates. Yes, our things, we start with 1100 kilometers per hour and we end up with smaller number. It makes sense that our constant acceleration is negative. Cool. Okay, and one last thing, let's find the TF. So TF, you can look at in your notes. TF is equal to V final minus V initial divided by AT. We know all of those numbers, so that would be this time in meters per second, okay? 222.222 minus 305.556 divided by that number we just found, minus 15,91056. Grab your calculators and obtain that that turn takes approximately 5.238 seconds. Bang! The end of the problem. Answer. And now I am looking forward to some questions. Yes, Jason? Sure, because I could use meters per second because 305.556 divided by 222.222 is exactly equal to, oh, shoot, sorry, the other way around, yes? This is exactly equal to 800 divided by 1100. If you want, you can in here, you can use this one. I don't care. It will be the same answer. Note that units will change because these guys are expressed in meters per second. Yes, so these guys are expressed in meters per second. Meters per second, meters per second. And these guys are expressed in kilometers per hour, okay? Kilometers per hour. They will cancel out regardless of what units you use, yeah? This will cancel out with this one, this will cancel out with this one. It will be just a scalar, okay? I hope I answered your question. Anybody else? I have a usual question, how do you like it? Is it digestible or it is abstract? I know that it is abstract, guys, yeah, but you also have abstract brains, yes? You can do it, you can understand it, I bet. Yeah, what do you think about it? How does it look like from your perspective? By the way, am I talking too fast? Sometimes, yes, no, sometimes, okay. I should slow down maybe, yeah. I just wanted to finish on time and we still have like 7 minutes. So you can ask me a question about that problem or do you want to do example number 3? Do you want to do it? Okay, let's do it. I'm not sure if we will finish this on time. However, even if we don't, please double check the solution on Canvas, okay? Because I think that problem is useful because it will show how to use this expression. Rho x is equal to 1 plus y dot squared, square root, to the power of 3. And in denominator, you have y double dot absolute value, okay? This example illustrates how to use this expression to find radius of curvature, okay? So even if I not make it, please double check the solution, okay, on Canvas. I don't know what will be on the exam, yeah? Maybe it will be a problem requiring this one, yeah? Okay, guys, so what do we have in here? Please familiarize yourself with the problem statement, but we did it before the discussion, yes? So we have our car traveling along this trajectory, yes? It travels along the hill, yeah? This is our trajectory, and we have expression for our hill here, yeah? Y is equal to minus 0.003 x squared. As you can see, our anti-coordinate system changes in time, yeah? And we have a velocity constant. We are on Earth, so we have gravitation, gravity, I mean, sorry. And they ask us to find the minimal speed so that car loses contact with ground. Yeah, so basically minimal speed so that car starts flying. Yes, at this point, at point 0, 0, at point Q. Okay, so let us write down our magical expression once again. V dot ut plus v squared over rho un. Okay, so what is this value, by the way? It is 0. Yeah, because velocity is constant. That simplifies the problem tremendously, because our A will have only one component. And now I would like you guys to tell me what is the requirement so that our car starts losing contact. Louder? I thought some of you were saying something. Starts losing contact with the ground. Yeah. Anybody wanna go for that? What value this should have? AN. This should, yes? Yes, exactly. It should overcome the gravity. Exactly. So AN should be equal to G. In other words, if you guys wanna talk like vectors, you can write in here that the requirement is A vector equals to minus GJ or J UN. Yeah, you can see that UN and J are opposite, points opposite directions at this point, yes? J points upwards, UN points downwards. Great. Okay, so we basically have this expression. And what is your name, by the way? John. Okay. V squared over rho is equal to G. So we have V is equal to rho times G. So we know G, but we don't know rho. And now, how to find rho? Tackle it with this. Yeah. Yes, Clara? Oh, because it will be like because if you travel along the curvature, yes, you will experience centrifugal acceleration. Okay, so basically you will be pushed this way, and this is function of velocity, as you can see. Yes, this is our centrifugal acceleration. Yes, so we just and always g acts this way. Yes, so if your velocity is some number, you can generate actually centrifugal acceleration that is also g, and this is the minimal speed, so that you will start flying basically in your car. Okay. So we have 2 more minutes. So I just would like you guys to use y equals to minus 0.003 x squared. Please find x prime, y double prime, and find them for x equals to 0, okay? And plug all of these values here. You can do it here right now even, 0.006x minus 0.006. So this is 0, 0, minus 0.006. Yes? So please plug these values in here. Okay? Find rho. Which will be, rho in this case will be magnetic value of minus 0.006, 1 plus 0 squared to the power of 3. And this is approximately, no, this is exactly 500 divided by 3 meters. Okay? And now we have now we know rho, now we know g, So we know V, yeah, because we can plug these guys in here, yeah. And the V is approximately 1.145,566 kilometers per hour. This is the end of the problem. Okay, thank you so much for today. Are there questions? No, I will stay here for 2 more minutes. Okay, you can ask me questions. Okay, so we did all the things. Have a nice weekend, guys. Thank you.